Okay, so what are we looking at? Okay, and we have these two separate orders and we know the totals, right? This one is $21. This one is $16. And what's the problem? We don't know how to split the bill up because we don't know how much individual things cost. And the thing that makes figuring that out difficult, even though we know the totals, is that there are two things we don't know, right? We're used to solving one thing we don't know. Like if this was $21 and I spent $21 on 6 tacos, well, I know how to do that, right? 21 divided by 6 and whatever that is how much each one cost. That's not a big deal. Similarly, if I spent $16 on one burger, like I know how much it costs then, right? The problem is that we have two things we don't know, but we've also got two separate pieces of information about how they relate, right? If all I had was one of these, if I didn't know this, and I just knew that I had 8 tacos and one burger and it was $16, there are infinitely many possibilities for how those could break down, right? Maybe tacos are $2 and if you buy 8 tacos, you get a free burger. Or maybe, it breaks down in some other way, like even, things that aren't like nice round numbers. There are infinitely many possibilities for how that works because what this is a linear equation, right? This is 8x plus 1y equals 16. That's a linear function, right? Once I take two of them and put them together, though, now we're talking about they're still linear, but system of two equations in two unknowns. So how can we write an equation that describes what's going on here? I'm sorry, say again. 6x. Okay, 6x plus 3y equals 21. Okay, so what's x? And really just, let me write this somewhere. Really, we're saying that x is the price for each one, right? The price per taco. And y is the price per burger. Okay, then 6x plus 3y equals 21. Now, again, that's a linear function, right? If you rearrange things and solve for y, that's some kind of linear function like this. Which again has infinitely many solutions because every point on that line is a solution, even the ones that don't make sense in a like real world context, like tacos are $100 and cheeseburgers are negative $50, so you get money back. Like this doesn't make any sense, but it's still on that line, right? Okay, how do we do the same thing with the other one then? 8x plus y equals 16. Okay, well, that's a different line. It's got infinitely many solutions. But when I look at both of them together, what do we get? A point where they intersect. A point where one of them is true at the same time as the other one is true. What's this then? That's our solution. That one point where they cross, and if you think about just taking two lines and sort of like dropping them randomly in the plane, right? Like two pieces of uncooked spaghetti or something, you drop them on a table. If I extend those infinitely, they're going to cross somewhere almost certainly, right? That one point is our solution. So one way to solve this would be to say, okay, well, what was it? 6x plus 3y is 21. Okay, thank you. And 8x plus y is 16. There they are. There's where they intersect. So 1.5 comma 4. What does that tell us about the system then? Or the solution or the menu? Tacos are $1.50. Burgers are $4.
I could have done that my entire high school career where I just plugged in the graph stuff.
Yeah, I guess. Sure. That intersection is the solution to the system. Okay, so one way to solve a system would be to do that. X equals 1.5. Well, I wrote it as 1.50 because it's money. Y equals 4, so tacos are $1.50. Burgers are $4. Now we know how to split the bill up, right? Okay. Desmos obviously you can just type stuff in, then click on the intersection. Calculator will do intersections as well. If you want, help with that, let me know. That's one way to solve the system though. And even when we're solving things by hand, as we're about to do, that's what's going on in the background, right? We're talking about two straight lines and finding where they intersect. Okay. How could we solve a system like this? Let me just copy it again here. 6x plus 3y equals 21. 8x plus y equals 16. It's pretty common when we're talking about a system like this to write them this way and put like a big curly brace. Curly braces always just mean this stuff goes together. So just to, really like underline the fact that we're talking about the same x and y here. Like we're talking about these things simultaneously. So how else could we solve a system like this? Like what could we do to actually like work out the solution?
Well, we need a single variable.
Okay, so how can we do that?
The two methods you have listed on there, substitution. Method.
Okay, yes.
Substitution.
Yes, there is a thing on the notes that says substitution or elimination, but what does that mean?
Substitution is we solve for one variable, like let's just say y, since y is by itself on the second.
Okay.
Solution, move everything over to one side. And so then we have a solution for y. Y equals 16 minus 8x.
Okay.
And then we go to the original. Do you want to?
No.
Go ahead, finish.
Hey, same team, guys.
Yeah.
Same team.
You replace the y on the equal 21 with the 16 minus 8.
Okay, I give up. I'm trying to resize the thing. It's not working. Okay, so we have a place in there where I've got, y all by itself. That would be pretty easy to solve for y then, right? Okay, so let's do that. Let's take this equation and solve for y. To solve for y, what would we need to do? Subtract 8x. Okay, so y is 16 minus 8x. Then what?
Then the other equation will be 6x plus 3 times 16 minus 8x.
Go to the other equation. And in place of y, I'm going to put 16 minus 8x. Is it important that we go to the other equation?
Yes.
Yes. One, just sort of conceptually why it's important that we go to the other one. I have to be tying these two pieces of information together, right? Like we just finished talking about the fact that if there's just the one order, then there are infinitely many possibilities. Like I can't solve it with just one. If I only use one of the equations, that's like I'm ignoring the other one altogether. There's not a distinct solution to that. So I have to tie the two equations together somehow. That's how I'm doing this here. I used one to solve for y. I plug into the other one to do the substitution. Now I've kind of tied them in together. The other thing is if you try to just plug this into the equation you just got it from, what happens? 8x plus in place of y, I put 16 minus 8x. And I get 16 equals 16, which is true, but not very helpful, right? Or, depending on how you move things around, you get 8x equals 8x, or 16 equals 16, or 0 equals 0, like some kind of identity that doesn't really tell us anything, right? We don't learn from. So I have to go to the other equation. Well, once I do that and substitute into the other equation, now what do we have? A normal equation, yes, thank you, Ellie, perfect. A normal equation, we've got a linear, because everything's first power, equation in one unknown, right? It's just in terms of X. If I had done things a little bit differently, maybe it would just be in terms of Y, like we don't care about that part, right? But it's in terms of just one thing. So solve it. Six minus 24, 21 minus 48. Thank you. And then X is 150. It's linear, so all we have to do is push stuff around and get X by itself, right? Now what? Yep, plug that back in. We have one of the things, we need to find the other thing that goes with it, so plug it back in. You can plug it back in kind of wherever you want. It doesn't really matter. Where would be a good place? Okay, here or here, since we already did the work, right? Like it doesn't really matter. It saves you a step, but plug it back in somewhere. I'm going to plug it into where we already solved for Y. So Y is 16 minus 8 times 150, which is 4. And then again, since this was, you know, a word problem, that means tacos are $1.50. Burgers are $4 is what's going on there. That's an ordered pair. So if I'm just solving a system with no like context, right? Like the stuff on the back here where it's just, you know, here's two equations, solve them. It's an ordered pair. So I'd probably write my solution as an ordered pair, right? 150 comma 4. Here we're talking about something, so I'm going to label them. Okay. That makes sense. Does anybody have any questions about that? That's substitution because we took one equation, we rearranged it a little bit just to make our lives easier, right? There's nothing like special about that. We're just rearranging. And then we use that to substitute or plug in to the other equation. That part's important, right? You'd have to tie the two things together. Okay, cool. Any other ideas about how we could approach this thing? Elimination for this one in particular is maybe going to feel like, hopefully that feels what we just did feels like fairly natural, like not a big weird extension of stuff you already know. Elimination might feel a little bit less natural for this one, but the idea is that we eliminate one of the things, right? We know how to solve for one unknown. I don't really know, we're trying to figure out how to solve for two unknowns. So, okay, well, how can I take these two things, these two equations, and mush them together so that one of the unknowns goes away? The way we do that is by adding them together or subtracting, maybe with scaling it also. Like you can, you know, do whatever you want to one side of an equation as long as you do it to both, basically, right? So what I would look for is decide, okay, what do I want to eliminate? Let's get rid of Y. Just because, no particular reason, right? Yeah, no particular reason. There's a little bit of a reason that'll become clear, you know, in a minute. I'm going to erase this if that's okay. Okay, so to eliminate Y, first I need the coefficients to match. Right now I've got 3Y in one equation and just Y in the other one. So if I want the coefficients to match, what could we do? Multiply this one by 3. That's the little bit of a reason that I'm choosing to get rid of Y instead of X, right? Then I only have to do that with one of them instead of with both. If I went after X, I'd have to get 6 and 8 to a common multiple. Okay, so if I multiply this by 3, I get 24x plus 3y equals 48. I'm not doing anything to the first line, the first equation. Just leaving it alone. I'm still kind of focusing in here. To do elimination, what we want to do is combine the two equations by addition or subtraction so that something goes away. Well, now I've got the y values lined up so they have the same coefficient. So how would I need to combine them to make y drop out or subtract, be eliminated? Subtract. Subtract, combine like terms, right? So just go term by term. 6x minus 24x.
Negative 18.
3y minus 3y.
Nothing.
And 21 minus 48.
Negative.
Oh, hey, that's only got an x in it, right? Now we're down to one unknown. I know how to solve that. Divide by negative 18. I get x is 1.5. Then again, once we have one of them, back up and find the other one. So I'm going to go back to either of these. We don't have like quite as good a place to get into it now, right? Because I didn't do the like algebra stuff on the front end. But I'm just going to go back to either of those and plug in. So 6 times 1.5 plus 3y is 21. That's 9. So 3y is 12. So y is 4. Oh, sorry. That's how elimination works. That's not the only way to do an elimination here. You could, if I wanted to get rid of x, I could multiply this by 4 and this by 3, take them both up to like 24, right? And then combine. If I'm thinking elimination though, I would look at this and see, okay, 6x and 8x or 3y and y. Okay, I can get away with, doing a little bit less to eliminate y, right? You get to the same place. I wouldn't really call either of those more difficult than the other, right? One is maybe a little bit faster sometimes than the other. Sometimes it's just kind of a toss up. We want to make sure that we're sort of comfortable with doing both because when we get, so for right now, we're just talking about straight lines, linear stuff. There, it doesn't really make a difference. Like either way, maybe you save a step or something. When we start talking about nonlinear stuff and there are x squared terms or y squared terms in there or both maybe, then sometimes we're a little more forced into doing one or the other because things aren't going to combine, right? If I have like x and x squared, those aren't like terms, so I can't combine those. So I maybe can't do elimination then, where I have to treat it differently. So that's why we're talking about sort of two different ways to do the same problem. Okay, anybody have any questions? Yeah,
Do we
Sam.
have to learn all, will we have like specific moments where we have to use each of these for the test?
No, I'm not gonna, on a test question, I'm not gonna say like, do this by substitution. I'm gonna say, solve it by substitution or elimination, right? Basically just solve it by hand somehow. And you can kind of go about it however you want. Again, for nonlinear stuff, if there's an x squared term or something like that in there, then sometimes you're kind of forced into one or the other. But for something like a test question, I usually try to write it so that you have, the option. So flip over to the back. There are 6. Above that line, there are 6 systems there. My directions, I said you can do whatever you want, but you need to do 3 by substitution and 3 by elimination. Obviously, like I don't have any way to enforce this, but that's the idea, just to get you thinking a little bit about when to do what or when one might be a little easier than another. So let's just take a look at one as an example and kind of think through that thought process, like when to do, what, how do I decide how I'm gonna go about this. Again, some of this is kind of looking, to the future and what's coming after break. What I want you to be thinking about is like why you're doing what you're doing. And also, maybe be a little bit clear, like write yourself notes, so that you have them later about why you're doing things the way that you're doing things. So looking at this, what do you think? Elimination? Why? Well, first, eliminate what?
X.
X? Why? I mean, WHY, sorry, or K. Okay. So eliminating X is going to be easier than getting rid of Y. Because we only need to change one. Because the coefficients are 4 and 2, so I can get 2 up to 4, right? And make them match that way. If I tried to eliminate Y, we would have to do some scaling on both equations, right? Because you got 3 and 5. I can take them both up to 15 and that's fine, but it's an extra step, which means it's what, 3 extra multiplications, which means 3 extra places that, maybe you make a little arithmetic mistake or whatever. And then, that spirals out on you sometimes. This is a place where, and especially again, like looking forward to where we're going, in the next few days. You make a mistake at the beginning and then like you just kind of feel like things are wrong, right? And then sometimes you start making other mistakes. So, basically what we're doing right now is just trying to reduce the amount of arithmetic we have to do. Why did we jump on elimination and not substitution?
Because we saw that we could do one step instead of like 2 or 3.
Okay, yeah, because I saw that I could do it in one step. Yeah. What would I be looking for that, might make me think right away, like, ooh, substitution? Okay. What would make substitution more challenging or messier here? No matter what you solve for, you're gonna have to move stuff around and then you're gonna have to divide. And then you're gonna be dealing with a fractional thing, right? So what would I be looking for that, would make me maybe jump on substitution rather than elimination?
A single variable.
A single, a thing that's got coefficient 1, right? Like this, right? I might see that and say, oh, substitution. Because I can solve for that by just moving the other thing over. I don't need to divide. Here, if I try to substitute, no matter what I go after, I'm going to have some kind of messy thing. Now I got to take that and plug it in here. So it's 5 times this fraction that's over 3. Like it's going to turn into kind of a mess, right? It doesn't make it wrong. You can still do it. It's just going to be like you're choosing to do it like the hardest way you possibly could, basically. Okay, so anyway, we decided eliminating X would be easier. Go ahead and do it if you haven't already. So, well, yes, that would have been smarter, but now I don't want to have to walk all the way back over there again. So we multiplied the second one by 2. because we're trying to eliminate X. I had a note about that, but then I erased it. We're trying to eliminate X, so we multiplied the second equation by 2. Now I've got 4X and 4X lined up. I'm gonna just check that I actually did the multiplication. 4 plus 10 equals 6. Okay, cool. It's, again, like there's enough going on that it's easy to make little mistakes like that. Now, if I want to eliminate these, how do we need to combine the two equations? Subtraction. If they were opposite in sign, like if I had 4X and negative 4X, then we would add instead, right? What we're worried about is getting the values to match, not necessarily the sign. So I'm going to subtract here. The book, by the way, insists on calling elimination addition / subtraction. Like, I don't know, but that just means that, we're doing the same stuff that we're doing. Okay, so I subtract 4X minus 4X is 0, which is good. That's what we set out to do. 3y minus 10y and negative 1 minus 6. So y is 1.
Smiley face, smiley face became a variable, right?
What?
Like the smiley face, right?
What's a 0?
Oh, so the smiley face stands for 0. That's what it is.
Okay. Fine. No smiley face for you. Okay, y is 1. Now what? Plug back in somewhere, right? Doesn't really matter. Nowhere's really going to be any easier than anywhere else. Plug in somewhere. So our solution to the system is the point negative 1, 1. You can check that by graphing, right? So I would just, grab Desmos, graph those two things real quick because you can type them in just like they are. All we're using that for is a way to check anyway. And then you should see the intersection at negative 1, 1. Okay? Everybody feel good about that? Okay, great. Y'all walk me through another one of these. I don't know. Number one, okay. Everybody have everything they want here.
So this one you can do by elimination because the coefficients are the same. You just have to add the two together.
Okay. So you want to eliminate y? Coefficients are already the same. That's a good point. Negative y, negative y. How would we need to combine the two equations to eliminate y then?
You have to
Subtract.
Try adding them. 6x plus x is, what's negative y plus negative y? Right, okay, so that didn't do what we wanted it to, right? It gave us another equation that still has x and y in it. So instead of adding, because they're exactly the same, subtract. Okay, good, I'm glad that came up. And again, just be careful, like make sure that you're doing the same thing all the way across, right? I'm adding the two equations together as a whole. That means I need to add like terms in sort of all, like 3 x, y, and the other, the constant term. Add everywhere. Sorry, we're subtracting here though. Subtract. Okay, so 6x minus x. Negative y minus negative y is what's happening there. So 0 equals 5. So x is 1. And then if x is 1, y is also 1. So our solution is 1, 1. Again, this is definitely not the only way to do it, right? It's a way to do it. This is a place where, you know, more than anything else, like the way you do it might be a lot different from the way you do it, and like, that's okay, right? This would also be a good one to do by substitution. Look at like the second equation, x minus y is 0. What does that mean about x and y? They're the same. So if you're doing a substitution, you get to replace x with y or y with x, either way, and you find one, and then you found the other one too, right? And like we see that obviously with what the solution is, but that would work too. Okay, cool. Everybody good? Yeah, okay. Now, two straight lines. Again, if I drop two straight lines in the plane, you know, like pieces of uncooked spaghetti, I just, you know, sort of drop them randomly. Probably they intersect at one point somewhere. But probably. What else could happen? They don't intersect at all. What would have to happen for them to not intersect at all? They have to be parallel. Parallel lines have the same slope, so they go the same direction, but different intercepts, so they start off, you know, apart. How would you solve this system? Okay, eliminate what? Okay. Let's eliminate y. Or eliminating, is all I like to call it. Eliminate y. How would we eliminate y? First one times 2. Okay. So 6x 4y equals 10. 6x 4y equals 8. Probably just in the process of writing that down, like you get a feeling for what's about to happen, right? If I'm trying to eliminate y, we would need to subtract because 4y and 4y are exactly the same. What happens when you subtract though? 6x minus 6x is 0. 4y minus 4y is 0. But 10 minus 8 is 2. So I get 0 equals 2. This is a contradiction. Right? It's a logical fallacy. It's not true. X and Y are gone. So there's nothing to like adjust that could make it work. It's just a statement that doesn't make any sense. Right? What does that mean about what's going on? Do it.
They're parallel.
They're parallel. There's no solution. How do we know they're parallel? 6x and 4y, right? They've got the same coefficients, exactly the same. Now, if you rearrange, what that means is that they have the same slope, right? This is a line in standard form, which we're not as used to looking at, but 6x and 4y, or the 6 and the 4, sometimes we call those direction numbers. Those are exactly the same. That means they have the same slope, but the other side, 10 and 8, those are different. It means they have different y-intercept. These are parallel lines, which means there is no solution. Sometimes, oh, yeah, sorry.
I actually noticed that it's saying one more thing is also a false equation because there's two more things.
That's true, yes.
Those are-
That's true. There are two more things, but they're kind of the same thing, but kind of not, which will make more sense in a second. Sometimes a system like this where there's no solution because we're talking about parallel lines, sometimes that's called an inconsistent system. You're not gonna like need that, but I think there might be one or two places where it, you know, shows up in the homework if you're reading everything. Because the lines are parallel, they don't intersect, that means there's no solution. What that looks like in the like algebra when you work things out is that at some point you run into a thing that doesn't make sense, right? That's what that would look like. Okay, and the second of the one more things, how would we approach this one? What jumps out at you?
You can eliminate
Okay, eliminate what?
y.
Why? Okay. If you see something different, then do whatever you see, like that's fine. To eliminate y, I need to multiply this one by 2. I'm doing a lot of multiplying by 2. That's not always what you do, right? Again, you probably start to get a sense for what's going on. Negative 4y and plus 4y. So if I'm going to eliminate y, what are we doing to combine them? Adding, because they're opposite. Negative 4y plus 4y is 0. But what else happens? 2x cancels 2. And 8 and negative 8 also cancel. So I get 0 equals 0. Which is also not really what I expect, right? What I'm hoping to get here is like x equals 5 or something like that, right? A conditional, just fact like that. Instead, I get an identity. Just a true statement, right? It's logically true, 0 equals 0. It doesn't have to be 0 equals 0. It could be, 2 equals 2 or 5 equals 5 or something like that. But it's independent from any kind of variable or unknown thing that can have a value. It's just a number fact, right? 0 equals 0. What does that mean about what's going on here? What could we fall back on if we're not sure? Let's go look at them. Was it x minus 2y? That says 27 is what? 4? And the other ones?
Maybe it's 2x plus 4y equals 8.
See what happened? What's going on? They're the same line, right? One of them's dressed up differently, right? But they're the same line. It's like the old Looney Tunes bit where it goes through the line once and then he comes back with a fake mustache on or something, right? It's that. It's the same line. They have the same slope, right? But they also have the same y-intercept, so they live in exactly the same place. What does that mean about what's going on? What are solutions to the system? Places where they intersect. Where do these intersect? Everywhere, kind of. There are infinitely many solutions, but is this a solution? No, just the line, the points on that line, right? Okay, so there are infinitely many solutions. And the solutions look like, well, take one of the equations. Let's take the one that was simpler. So the first one, x minus 2y equals 4. If x minus 2y equals 4, then x is 4 plus 2y, right? So all of these solutions look like this. What we're doing is sometimes called parameterizing. We're writing kind of like a little, formula for finding points that are on that line. So what this says is if you give me a y value, right? This is a straight line. It's a linear function. It's defined everywhere. If you give me a y value, this will give the x value that sits on that line, right? That goes with that. So if you say, hey, y is 5, I would say, okay, 2 times 5 is 10, 14 comma 5. That's a point on these lines that solves that system, right? Not everything works, 0, 0 doesn't work, right? But 0 and 4, 0, that does solve the system, right? That works for both of them. So that's what this is doing. When there are infinitely many solutions, we'll, also do this thing and figure out like, hey, here's what they look like. Right? And again, all I did to get that is take one of the equations, like the thing that looked to me like it was gonna be the easiest to get to. X minus 2y equals 4, I solved for x. Now I've got that in terms of y. The problems in the homework, I think the way these are kind of set up, it'll give you like a blank here and like y will already be there. So, okay, write it in terms of y then. That means go solve for x somewhere in terms of y. You could do it the other way. I could write them as x comma, whatever I get when I solve for y in terms of x. Minus x over 2, I think, something like that. I don't know, I'm doing it quick, but this kind of thing, like that would do the same thing, right? Now you give me an x value, this will give you the y that goes with it, right? It doesn't really matter. All we're doing is saying, here's how you can find points that solve this thing. Okay. Anybody have any questions about anything? That's a good question. Something like the 4th of December? Yeah, I think all the chapter 7 stuff, and I'll try to remember to go check this, but I think all the chapter 7 stuff is due like right at the last day of class, the 4th. So, okay, well, that's all I have for today. Y'all have a great break.